Good evening, sir. We are from Group 2 and our presentation topic is Chapter 6, Resource Access Control. First, I will introduce my group members. So my groups consist of 7 members. I'm Ng Chin Huan and my group partner is Arif, Jun Naim, Nazrul, Amizan, Izati, and also Pavinesh. So basically, there are 3 types of resource. So the first one is hardware device, such as the sensor and actuator. The second one is disk or memory capacity and buffer space. The last one is software resource, such as the mutex, logs, and queues. Now, this is the task state diagram. So basically, it consists of 3 states, which is running, ready state, running state, and also waiting state, or sometimes we call it as block state. So task state, task move from ready to running state when it has been selected by the scheduler. So this means that the task preempt other tasks since it has the highest priority among the ready tasks. So when a currently running task preempt by other tasks, it will move back from running to ready state. So a task is in the block state when it need to wait some other resource before it can proceed. Now, we go into the priority inversion problems. So priority inversion is an undesired situation where a higher priority task is blocked and has to wait longer than expected because lower priority tasks are using the CPU. So in the next slide, we will show one example of priority inversion. So for this example, we can see that T1 has the highest priority, T2 has medium priority, and lastly, T3 has the lowest priority. So the problem is T1 and T3, they share the same resource. We name it as S. So at A, T3 lock the share resource and enter its critical sections. So when we arrive at B, T1 preempt T3, and T1 will try to share resource S. However, T1 will fail because T3 is still holding the resource in its own critical section. So we can see here, C, show that T3 continues its execution because T1 cannot start its execution. So after that, for this, in this scenario, T2 preempt T3 and is ready to run. Since both of the tasks do not share the same resource, the scheduler can select T2 to run. So this situation will leave the T1 waiting not just for T3, but also T2 to finish executing. So lastly, T1 can only be executed when task 3 has run to completion and release the shared resource.
So the purpose of this priority inheritance protocol is to solve the problem of priority inversion. So as you may know, the priority inversion is when the lower priorities block the higher priorities from being executed. So this is priority inheritance is the way of preventing that or solving that. So there are a few benefits of priority inheritance protocol. So number one is ensures higher priority tasks and unduly delayed by the lower priority tasks, which I mentioned earlier. So the second one is to reduce overall task latency and improve system responsiveness. So how does priority inheritance protocol work? So let's say given the circumstance, task B have a highest priority, task A with the lowest priority, log task B. So the task A will temporarily inherit the priority of task B. So let's say if the A is the biggest priority, task B will run first because it blocked the task A. So that's priority inheritance is also sensitive. But unfortunately, even though priority inheritance protocol can solve the priority inversion, but it still does not prevent the deadlock. So priority inheritance is sensitive, meaning that if let's say we have 3 tasks, we have task A, task B, task C. So task A being the highest priority, task B in the middle, and task C with the lowest priority. So let's say if task C block task B, cause a priority inversion, means that task A will be blocked. So what will happen? What it will do is task B will take task A priority. After that, the task C will take task B priorities. So it will invert task C will have the highest priority and followed by B and also A. So this is which I mentioned earlier. Priority inheritance protocols could not prevent that lock. So like this situation here, we have a task operation sequence on critical section. So T1 lock and T1 CS2 lock unlock CS. As you can see, so this is the time task and action. So right here, start execution. So T1 locks the CS2. And after that, it was being activated and preempts T1 due to its higher priority. So lock CS1, attempt to lock CS2, but it's blocked because as you can see, T1 has lock on it already. So after that, in here T5 time, it inherit the priority of T2 and start executing. So attempt to lock CS, but it's blocked because T2 has lock on it. So both of these tasks cannot be proceed because it was blocked within each other. So priority in conclusion, priority inheritance may does help to prevent the task from being blocked, but it still does not prevent that lock.
So for priority ceiling protocol, each semaphore has a priority ceiling. Priority ceiling of a semaphore is the highest priority of all tasks that may lock it. The value is used to control access to critical sections and prevent priority inversion. For critical section entry condition, task T1 can enter its critical section only if its priority is higher than the priority ceiling of all semaphores currently locked by other tasks. If T1's priority is not higher, it is suspended until it can safely enter the critical section. For blocking and priority inheritance, if task T1 is blocked because it cannot enter its critical section, the task holding the semaphore with the highest priority ceiling that is blocking T1 is considered to be blocking T1. For priority inheritance, the blocking task inherits the priority of the blocked task. For preemption condition, a task can preempt any lower priority as long as it is not attempting to enter a critical section. If T1 is attempting to enter a critical section and is blocked, it temporarily elevates the priority of the blocking task. For deadlock prevention, priority ceiling protocol, also known as PCP, prevents virtual deadlock among tasks. A task can be blocked by lower priority tasks at most one. For an example, from time T0 to T2, tasks run smoothly without any blocking. This period shows normal operation where tasks can access resources freely and efficiently. At time T3, T2 tries to access CS1 but gets blocked because T1 is using CS2, which has a priority ceiling equal to T2's priority. This blocking ensures that T1 can finish its task without being interrupted by T2. Since T2 is blocked, T1 temporarily inherits T2's priority to finish its task faster. Once T1 completes its work and releases the resource, T2 can proceed. This process helps prevent deadlocks and keeps the system running smoothly.
So the first one is about Mars Pathfinder mission context. On July 4, 1997, the Mars Pathfinder mission used VxWorks RTOS. RTOS stands for Real-Time Operating System. The VxWorks is used to control network and test the major equipment. And then second is scheduling. So the system uses preemptive priority scheduling, which involves tasks being assigned priorities. Higher priority tasks preempt lower priority. And third is about priority inversion. T1 for information bus task, which means the highest priority, and T2 is for combination task, medium priority, and last is T3, which is meteorological data gathering task for lowest priority. So this is a Mars Pathfinder accident. So what is the Mars Finder do? To collect data and navigate or capture image at the Mars. So the problem is due to priority inversion, cause the spacecraft to reset itself several times. So this reset triggered by special system process is called watchdog. So watchdog is to design the reset system if it detect any problem. So because of this priority evasion, the same task took longer to complete than they should have, and then causing the timing issue. Example of priority evasion on Mars Pathfinder. As you can see, this is the high priority task, and this is second, and this is lowest priority task. So assume that the lower priority task start first to execute, and then is acquire a resource, which means we call a log new text. So after that, we find another available task to be executed, and then the higher priorities start the execute and become active, and then the high priority require a resource and is cannot continue because it's held by the lowest priority. So after the high priority is blocked, will continue to find another task to continue the execute. So assume that the middle of this start to execute, and then at the last point, the lowest priority task release the resource. After lowest release resource, connect to the high priority task, and then high priority task will start to continue the execution. The priority ceiling elimination. So when the task unlock a semaphore, its priority is immediately erased to the priority ceiling of the semaphore. Deadlock avoidance. The protocol have avoid deadlock by ensuring that tasks cannot hold and wait for resource in a way that create circular dependency. For the registration, a task cannot suspend its execution within a critical section.
Blocking time BI is encoded by task, which is equal to TI by lower priority task, can be modeled by increasing the TI's utilization by BI per PI. Earlier deadline is equal to DI lesser than PI can also be modeled as blocking time for EI equals PI minus DI. Net increase in task, TI's utilization is BI plus EI per PI. So this is the modeling blocking time earlier deadline. It's an example. So we have task 1, 8 is the PI, 7 is the DI, and 2 is the C. It's being blocked by B1 is equal to 3. So E1 equals P1 minus D1, which in this case is 8 is our initial PI and 7 is our initial DI. So 8 minus 7 is equals to 1. 1 is our E1. So net increase in task 1 utilization equals to B1 plus E1 per P1. So our B1 is the initial amount, which is the blocking is 3, plus E1, which is the answer for P1 minus D1, which is 1 per 8. The official P1 value is equals to 0.5. So task 1's net utilization equals to C1 per P1 plus B1 plus E1 over P1, which in this case, the middle number just now is our C1 per P1, which is 8, plus with 4, which is our answer for the P1 plus E1, which is 3 plus 1 equals to 4, over P1, which is 8, equals to 0.75. Modeling blocking and earlier deadline content. Schedulability check, sorted as task 1, task 2, task 3, and so on. If let's say we have 10 tasks, so it's until T10. Sufficient but not necessary. Completion time test, exact equals to analysis. Earlier deadline, which is D1, DI lesser than P1. Case, same as DMS, exact analysis. Blocking time, which is BI. Case, let's say CI equals to CI plus BI. While calculating the WI T for the task TI, we use CI for task TI, and for all together higher priority tasks, TJ simply use CJ. So this is the resource external control. I give an example. So in task TI, we have 3 tasks. So you included the CI, PI, CI power of X, CI power of Y, CI power of Z. So for 3 tasks, for task 1 will be 2, 8, 2, 0, 0. Task 2, 4, 12, 0, 4, 0. And task 3, 2, 6, 1, 1, 0. So CI power of X, task duration before entering the critical section. CI power of Y, critical section duration. And CI power of Z equals to task duration after the critical section. So to calculate CI will be equals to CI power of X plus CI power of Y plus CI power of Z. In RMS terms, it will be first task 3, and then followed by task 1, and followed by task 2. So these are the schedules of RMS schedule. So in this example, direct blocking of task 3 by task 2. So task 3 is preempted. So first the task 3 will come because it has the higher priority, followed by task 1 and task 2. So after the task 2, we have a period. So task 3 have to act first, and then followed by task 2. Because why task 1 didn't come? Because task 1 has the medium quality, and also task 2 is not completed. That is why task 2 came in first, followed by task 1, and back again to task 2, and then a new period. Again, task 3, as task 3 was not completed in the previous schedule, and followed by ending with task 2. The second one, RMS schedule with priority inheritance protocol, direct blocking of task 3 by task 2. And also we have an inheritance blocking of task 1 by task 2. So in this case, as task 3 has 2 space, so task 3, then task 1, task 2. Task 3 will preempt back, come in the new period, followed by task 2 again. Because as task 2 was not completed 4 spaces, that's why task 2 preempted task 1 as missing deadline, followed by task 3 and task 1, because task 3 has 2 spaces but only 1 came in, and then again task 1, the new period, task 3, and ended by task.
Okay, first one is the basic priority ceiling protocol give a good performance, but defining the rule are complex. Also, can result in high context switch overhead due to frequent blocking if many job content for resources. And this has led to two modification to the protocol, which is the stack-based priority ceiling protocol and then the ceiling priority protocol. So next slide. Okay, stack-based priority ceiling protocol. Based on original work to allow job to share runtime stack, extend to control access to other resource. They have three to defining rules. So first is ceiling. When all resources are free, equal to pi t equal to ohm. So pi t is update each time resource is allocated or free. Pi t is current priority ceiling of resources in currently use. For ohm, not existing lowest priority level. For scheduling, after the job is released, it is blocked from starting execution until its assigned priority is higher than pi t. So non-blocked job are scheduled in preemptive priority minimum. Tasks never save here. And then allocation. Whenever a job requests a resource, is allocate the resource. And the allocation rule look ready, but scheduling rule is not. Okay, for the state-based priority ceiling protocol, consider an example system with the parameter are shown on the right. On the right, like this. So job 1, job 2, and job 4 and job 5 attempt to lock their first resource after 1 unit of execution. So okay, we go to the job 1. So we know 7. So we go to the 7, and then the execution is 3. 1, 2, 3, and then critical section is 1. So that's mean for the job 1 is done. Oh, we go to the job 2. Job 2 is 5. 5, 3, 2. For 5 is the starting. So starting is 5. The execution is 3. So 1, 2, 3. And the empty right is from the job 1. So for job 2 is done at 11. So we go to the job 3. Job 3 we know the attempt to lock is 4. And then job 3 is execution is 2. So 1, 2, and then at the end at 13. So job 3 is done. We go to the job 4. We know job 4 is 2 from this job block from starting since is 2 for job 4. And then we go for the execution. We know execution for job 4 is 6. 1, 2, 3, 4, 5, 6. So they have a 4 critical section. That means the critical section for job 4. And then consider from starting is 13 until 19 is job 4 execution. So job 4 done. Oh, we go to the job 5. Job 5 is 0 and 6. So starting is 0. So starting 0, we go to 0, 1, 2, 3, 4, 5. And then we go to the 19 and 20. So the job 5 is done at 20. So this is example with the system with parameter I show on the right. Okay, next. Okay, next is state-based priority ceiling protocol with three characteristics. They have three characteristics. When the job start to run, all the resource will never need are free. So no job ever block waiting for a resource once its execution has begin, and imply low context switch overhead. So number 2, when a job is preempted and resources the preempting job will require are free, ensuring it will run to the completion. So this can make that lock can never occur. So for number 3, longest blocking time probably not worse than the basic priority ceiling protocol. So not worse than the duration of one critical section.
In maximum blocking time, there are priority ceiling protocol that use in avoidance blocking. The first one. The second one is using a direct blocking. So what's the difference between avoidance and blocking? Avoidance blocking and direct blocking. Avoidance blocking and direct blocking. So the first one is direct blocking has a low priority job that lock resources, and lastly the avoidance blocking use prioritize the ceiling rules, deny any access. Next, we go to resource types and locking. There are 4 types of resource locking. Resource types and locking. So there are 4 resource type and locking. The first one is files, devices, network interface, and also first one is program object and data structure. So specifically in program object and data structure, there are 4
the four object in data structure. So the first one is semaphores, mutexes, condition variable, and message queues. So for POSIX, divided into two types. POSIX, which is semaphore and mutexes. So semaphore has two types, counting semaphore and also binary semaphore. So for 0 to 0 for lock, 1, 0 for lock, 1 for unlock. Mutexes. It has a higher level of locking mechanism for real-time apps, control priority during resource access. Message, signal, and event. So other than controlling access to the resources, tasks also often need to communicate information to other tasks. Implement using a shared data structure. So for example, a queue protected by mutex and conditional variable. Communicate with other tasks with the explicit synchronization step. So for example, send another task a message. Signal another task that an event occur. So for example, like we use system interrupt. So system want to send message to system by using interrupt. So that's the example of send another task a message. So that's all from us. Thank you very much.